All right, this is page 2 of 2279. Again, we're working on universal gravitation. More graphs. Which graph best represents the gravitational force between 2 point masses as a function of the distance between it? Again, you look at what the equation is when you want to know the relationship. You don't just know these things. You don't just guess. The relationship between two masses is this, where big G is the gravitational constant, 6.67 times 10 to the negative 11. Doesn't matter for this question. It's constant, meter squared per kilogram squared. M1 and M2 are your two masses, and R is your distance center to center between them. So as you move the masses further away because of this inverse relationship, you know that the force is going to go down. As the masses get bigger, because they're in the numerator, the force is going to go up. If you bring them closer together, the force is going to go up because of this inverse relationship. So really what we're focusing on is how is this related to this. I can rewrite this, and you may or may not like this, but it's proportional to 1 over r squared. Basically what that's saying is these things are all constant. The only thing that matters in terms of what happens to the force is this, and this will give me a picture of what the graph looks like. An inverse relationship, when you graph it, decreases like this. It is not a straight line like this. That is a negative mx, a negative linear slope. So of all the answers here, it looks like, answer D is the correct one, which makes sense. As you go further away, the force of attraction decreases between the two of them. All right, this picture gives you a lot of information, and it's a little unfortunate because if you just focus on what the question is and not all the useless information that they give you here, the magnitude of the force of the satellite on the Earth, the magnitude of the force of the Earth on the satellite, if you compare those. Basically what it's saying is how much force does the Earth pull on the satellite and how much satellite force does the satellite pull on the Earth. I mean, you can use this equation if you want and show that this, if 1 is the satellite and 2 is the Earth, if I wanted to find the other force, all I'm doing is basically rearranging the order of the multiplication, which doesn't change the answer. They're both the same. Or you could just use Newton's third law for every action, equal and opposite reaction. So that is a trick question. All right, next question. Gravitational force of attraction F exists between 2 point masses A and B when they're separated by a fixed distance. So basically you have Fg equals big G, mass of A, mass of B, divided by some distance squared. And it gives you a force, Fg, whatever that number is. Here's one of those what if questions. If mass A is tripled and mass B is halved, so our new force, Fg new, is equal to big G, triple one mass, and halve the other mass, and keep the distance the same. The new answer here basically has 3 halves out in front of the old answer. So your answer is 3 halves of your old answer. So 3 halves of F. Next question, another what if. 2 point masses are located a distance d apart. The gravitational force of attraction between them can be quadrupled by. Well, you can change the masses, but that's not in any of the answers here. They all have d. So we have to focus on how is Fg related to d. D is just the letter they're using for R. This is going to be similar to what I was talking about above. It's proportional to 1 over, I'm going to just call it d squared. So if I want them to quadruple the force, if I double d, that would produce a factor of 4, but it would be 1/4, not quadrupling. So what I have to do is I have to halve d. That halve, when I quadruple it, becomes 1/4 in the denominator. Fg would be proportional to 1 over 1/4, and that, when it goes to the numerator, becomes 4 times. So you got to bring them closer together, and closer together by a factor of 1/2, because remember it's a inverse square relationship. All right, next question. As the mass of a body increases, the gravitational force of attraction on the Earth increases. Pretty simple question there. And if the distance between a spaceship and the center of the Earth is increased from 1 Earth radius to 4 Earth radii. This is a weird question. Basically, your spaceship is here. And this is 1 Earth radius. What happens if I go all the way out here and I'm at 4 Earth radii? Again, it's the same thing where the weight is proportional to, or the force of attraction, 1 over r squared. If I'm quadrupling r, I have 1 over 4r squared. My answer is 1/16 of my old answer. So the answer is going to be B. 1/16 is great. Thanks for listening.